Hi, so let's go over this problem from the textbook, and it's a little bit involved, but it's a nice exercise. What we have is a particle that's moving along the x-axis, and then we are asked some questions. Velocity, critical points, let's see, intervals of increasing and decreasing, but then D and E, they at least read a little bit different. We want the total distance traveled, and then we want where is the particle farthest to the right and to the left. So let's begin. First of all, part A. Well, the velocity, this would just be the derivative. This is 12t cubed minus 60t squared minus 48t plus 240. And this is, without a doubt, let's see, it's in meters and in seconds. So this is in meters per second. Now this is perfectly fine. Here is part A, but you see, I'm going to have to set this equal to 0. And so I need to factor this. And this, I think, is one of the harder parts of the problem. We have this cubic, which we need to factor. And that is usually not something that we are used to doing. But I can first factor out a 12. I have t cubed. And then I have minus 5t squared. And then I have minus 4t plus 20. Now, let me just take these first two terms and factor out what's in common, and then I'll take the second two terms and factor out what's in common. And this might seem strange, but we will see it leads us down or leads us to the right answer. So I can factor out here a t squared, and then I get t minus 5. Now, these two, let me just factor out a minus 4. And I get t minus 5. And this is when we realize that this was the right way to go about it, because here, you see, now I can factor out a t minus 5. So I have 12, I have t minus 5, and then I have t squared minus 4, which is t plus 2, and t minus 2. Now I have the derivative factored. And so my critical points are, well, where the derivative is 0, which is 5 minus 2 and 2. But also look, we are on a closed interval, which means also the endpoint. So this would be minus 3 and 10. Okay, so this is letter B. Letter C, increasing and decreasing. So I make my number line. Here are the endpoints of my interval, minus 3 and 10. And then here were the places where the derivative was 0, which was minus 2, 2, and 5. And I see my intervals here. If I think about open intervals, this would be open, minus 3 to minus 2. This would be minus 2 to 2. This would be 2 to 5, and 5 to 10, like this, okay? And then, now, all of a sudden, this problem is like ones we have done, because we need to just pick a point in each interval and test. So here's one interval, here's one, here's one, here's one. And we test the derivative to see if the derivative is positive or negative on the interval. Okay, so here will be t, and then here is the derivative. And this is, I'll write it as x prime of t. It is the velocity, but we see it as the derivative here. And then, let's see, I need a point in each interval. Maybe I will do this in red. Here I can pick, for instance, minus 5 over 2. Here I can pick 0. Here I can pick 3. And here I can pick 6. So I have t equals minus 5 over 2, 0, 3, and 6. And I'm interested in the sign, plus and minus. So here, this is, let's see, negative, negative, negative. The derivative is negative. At 0, we have negative, positive, negative. The derivative is positive. At 3, we have negative, positive, positive, negative. And at 6, we have positive, positive, positive. Okay, very nice. So we know we have, let's see, minus. This means my function x of t is increasing. And increasing here is motion along the x-axis. So increasing means you are traveling in this direction, right? But increasing, everywhere we see a plus, which is this interval, and this interval. And then it's decreasing, everywhere we see a minus, which is this interval and this one. Okay, so far, except for the factoring part, A, B, and C have been reasonable, just like things we have been practicing in class and in homework. Okay, now, I think I'm gonna do this a little bit differently. So I first will do E, and then I will come back and do D, okay? That's my personal choice. So E, what we want here is when is the particle farthest to the right and left. These are times farthest to the right and the left. Let's think about this here. Well, when my particle, let's see, this way is left. So this way, farthest to the left. This says the position is the smallest it can be. So this one here would be the time corresponding to a global min. And similarly, farthest to the right, that's this direction. Think about this way. Then along an x-axis, it's the largest that the position function is. And so this would be the time corresponding to a global max. And so this is what this is asking us for in E, really, is asking for the t values corresponding to a global min and global max. Okay, well, we know how to calculate such things. Here, we don't need the increasing, decreasing, etc. All we need are t, and then we need this. This is the, I'll put it in quotes this time, but I always say it's the y value, even though we're thinking about x of t. Okay, so, and the t values that we use, they are all right here, my 5 critical points right here, okay, which include the endpoints, of course. So 5, 2, minus 2, minus 3, and 10. 5, 2, minus 2, minus 3, and 10. And now here is when I will use some software, because all I need to do is just evaluate the function. X of 5 is minus 24. X of 2 is 273. X of minus 2 is minus 367. X of minus 3 is minus 152, 10, and this is big. This is 10,001. Okay, so we see, looking at this chart, we see the highest y value and we see the lowest y value. And so it will be, now we go back and finish the problem. The particle will be the most to the right at t equals 10, and it will be most to the left. This is our, we see it, global min at t equals -2. And this is the end of part E. Okay, now let's go back. I'll maybe make this a little smaller and we can do part D. We want the total distance traveled. Okay, well, we want to use this information. So maybe let me copy this part. And paste. This is what we want to use here. I know where my function, look, my function decreases, and then it increases, and then it decreases, and then it increases. And it doesn't look exactly like this, but this is what's happening. Decreases, increases, decreases, increases. And I want the total distance traveled. And how can I do this? Well, what I want to do is find the distance traveled here, and then find the distance traveled here, and then find the distance traveled here, and then here, on these 4 different intervals, and just add it all up. What we want, first the function decreases. And so the distance traveled here will be x of this minus x of this. We take the larger one minus the smaller one. This is, this is the total distance traveled on this first piece. This total distance traveled is here, okay? And then the total distance traveled on the next piece, well, for the increasing function, I would take x of 2 minus x of -2, and this would give me the total distance traveled here. You take the larger one minus the smaller one. That's the distance traveled on one sub-interval. And then again, I am decreasing. So the total distance traveled here, we would take the larger one, which is x of 2, subtract off the smaller one, which is x of 5. Okay, that's here. And then finally, on the last subinterval, it's increasing. So the larger one is x of 10, and subtract the smaller one, which is x of 5. And this is another, as I mentioned, this is another interval where the function's increasing. Okay, so what's underlined in yellow, those are the intervals where it's decreasing and it's the total distance traveled. Underlined in pink, that's where it's increasing and it's the total distance traveled. We just add all of these up. Now, let's see. What do I have for these different values? We get, this first one is 215, and then plus, the next one is 640, and then x of 2 minus x of 5 is 297, and then x of 10 minus x of 5 is 10,025. Okay, I add these numbers up and I get 11177. This is in meters. And this is our total distance traveled. This is part D, and this ends this problem from our textbook. Okay, well, thank you very much.